Welcome to the walkthrough for problem 2 of Spring 2021 Midterm 2. We're going to go over this heaps and tree traversals problem. Suppose we have an array heap that holds integers, and it uses the array representation from class and discussion, also known as tree representation 3P in lecture. And recall that in this representation, the leftmost item is unused, which is why we have this little dash in this box, just to show we're not really putting anything there. It's a placeholder to make our indexing easier. And now we're going to consider a heap with the following underlying array. Suppose we perform a pre-order traversal of the heap represented by this array. What will be the last value in the pre-order traversal? And so immediately I see this, and I think that we should draw the underlying tree because it's a lot easier to work with and easier for us to visualize. And one way we can construct the tree is just by going in level order. And so we're going to see 5 is on top, 5 has 2 children. Well, those would be 4 and -1. And then the next things in order would be 5, 6, 0, 0. And so this is just what I mean by level order, is that the array is conveniently laid out for us in this pattern. And the last thing is 10. And so we can go across and just construct this array construct this tree by looking across in order and filling in the spots as they should be in the tree. The other way we could maybe visualize this or construct this visual would be to do the proper indexing thing where you'd say, okay, 5 is at index 1, so its left child will be at index 1 times 2, and its right child will be at index 1 times 2 plus 1, which would be index 3. And so we'd put the left child here and the right child there. And then we'd say, okay, the left child of this item or the thing at index 2 is going to be 2 times 2, which is the thing at index 4. And so we can say, okay, 4's left child is 5. And then we'd say the right child of the thing at index 2 is going to be at index 2 plus 1, so index 5. And we see indeed the right child of 4 is 6 at index 5, and so on and so forth. I personally think just going through in level order and filling in the heap as we go is much simpler than doing the array map, but whatever makes most sense to you is definitely what you should go with. And so we've constructed this underlying tree, and now we want to know what happens if we do a pre-order traversal. What's the last value we're going to see? And I'm going to recall or remind you all that there is an awesome hack we can do to make pre-order traversals super fast, as well as post and in order. And the way we do it is we draw a circle around our tree, hugging it closely. And we always say the pre-order traversal order is going to be the order in which we pass the left side of nodes on our little circle. And so we'll see what this means. Our pre-order traversal, starting at the top, would pass the left side of this 5 node first. So we visit 5. Then it passes the left side of this 4 node or vertex. Then we pass the left side. Oh, sorry, I realized I was dropping the negative sign, but this top one is a -5. Then we drop or pass the left side of this 5 node. We pass the left side of 10. We pass the left side of 6. Then we come back up, and remember we're hugging tightly. And we pass the left side of -1, the left side of 0, and the left side of 0. Then we come back up, and that's it. We've reached the top again. And so the pre-order traversal is going to see 0 last, and that is our answer. Another way to do this, if you maybe are uncomfortable with this little drawing hack, I think it's super useful, and I would love for people to use it and appreciate it. But another way that we could do this would be to more properly perform DFS, maybe with a underlying stack or something of the sort. And so we can imagine if we decided to explicitly write out this stack, we would start at -5. And so I'm going to say the DFS pre-order, I'll write here, and the stack, I'll write here. And so we see, okay, we put -5 on the stack, and then we pop it off the stack, and so it's been visited. And while we're popping it and we're looking closer at -5, we see it has some children, 4 and -1. And so we will go visit 4 and -1. And then we pop 4 off the stack. And while we're popping off 4, we see 4 has children, 5 and 6. And so again, in a stack, we always push and pop from the top. So these get put above -1 on this stack. We are pushing and popping both in this order. And then we pop 5 off the stack. And while we're visiting it, we see, oh, 5 has a child, 10. And so we push that onto the stack. And then we pop off the stack. And so we pop 10 off, and we see 10 has no more children. So then what's the next thing to pop off the stack? Well, it's 6. And so while we're looking at 6, we see, oh, 6 has no children. Okay, we can move on. And so we continue to pop the next thing off the stack. And now we're popping off -1, and we're seeing it has those children, 0 and 0. And so we'll put 0 and 0 on the stack. And then we're going to pop and pop. And those don't have children, so it stops there. And so we see that even if we do this explicitly with the stack, we still get the same answer. And so both approaches work. I think the drawing one is honestly a little faster. It just requires that you understand the deep, but it is important that you like understand how it works underneath and how the stack representation and a more proper run through of DFS reorder works. And so now we want to know, what if we do an in-order traversal of the heap represented by this array? What will be the last value in the in-order traversal? And so we're going to go ahead and do this whole hack again, except this time we're going to notice that for in-order traversal, we mark a node when we pass by the underside of that node or vertex. And just to be clear, if this is the vertex and it's got a little smiley face, we say the underside, we just mark it when we're passing right under there. And so we're going to go ahead and draw our little circle. And we haven't passed the underside of any nodes yet. And whoop, the underside of 10, right? We're directly underneath it. So we mark 10. Then we're coming and whoop, we're underneath 5. We keep going and whoop, now we're under 4. And then we keep going and whoop, now we're under 6. And now we're under -5. And then we keep going and now we're under 0. Oh, and now we're under -1. And now we're under 0. And so the last thing we visited in this inner traversal was 0. Just like before. And so that was our little hack, our little circle hack that made life so much easier. Again, another way we could do this would be by explicitly doing that DFS. And the way I honestly like to do DFS in order is a little different. I like to start at 5 and just say, okay, visually, have we marked all of 5's left children? No, we haven't. So we'll go down. And then we say, okay, visually, have we marked all of 4's left children? No, we haven't. So let's go down. Have we marked all of 5's left children? No, we haven't. Let's go down. And then we say, have we marked all of 10's left children? Well, yeah, we have. So we can mark 10 now because 10 doesn't have any left children, right? And then we go, okay, now we're allowed to mark 10's right children because we marked 10. But 10 doesn't have any right children, so it's not super relevant. And now that we're completed with 10, we can go back up to 5 where we left off and go, okay, where we leave off, 5, have we marked your left children? And we have, right? We've marked 10. So we can go ahead and mark 5. And now that we've marked 5, we're allowed to go visit its right child, but we see it doesn't have any. We come back up to 4 and we say, okay, are we done with your left child? And we are. So now we can mark 4. And now that we've marked 4, we're allowed to go visit the right child. And I just want to remind everyone that in order, you just mark the left, then mark you, then mark your right. So we mark 4, and now we're allowed to go visit 6. And at 6, we say, okay, you don't have any children. So it's easy peasy. We come back up to 4 and we're all done here. Now we come up to -5 and we go, okay, are we all done with your left children? We are, so we can mark -5. And now that we've marked -5, we're good to go and start looking at the right child. And so we go to -1 and we say, have we marked all of your left children? And we have not yet. So we go to the left child and we say, okay, 0, have we marked all your left children? Well, you don't have any, so technically whatever, sure. And then we say, okay, we mark 0 now. And then we're allowed to mark rights or zeros right children, but it doesn't have any. So we're all done with 0. We come back up to -1 and say, have we marked all of your left children? We have. And so we can go ahead and mark -1 now. And now that we've marked -1, we're allowed to go look at the last child or the right child. And that is the whole DFS in order. And so again, that just confirms what we saw earlier with our little hack, that the last thing we visit is 0. And so now, suppose we are using our heap to represent a priority queue. If we call removeMin on the heap above, where will the 10 end up after the removeMin has completed execution? Assume it works as described in lecture and discussion. And by completed execution, we mean the entire operation is done, and the array again obeys our heap properties. And so I just erased the array so we could maybe more clearly draw things out, because we're going to do a little before and after moment. And so this is the before. And we want to know what happens when we remove -5. And so if we recall, when we're doing heap deletion, we get rid of the thing at the top. And instead, we replace the bottommost, rightmost item. That's what we replace it with. And so we go to the heap and we go to the bottommost row, which is this one. And we pick the rightmost item, which in this case is 10, because there is no item to the left of 10, right? And so we go, 10 is the rightmost because, there's nothing here, right? If there were, then we'd pick the thing to the right. But 10 is currently the most to the right because there's nothing else there. And so we're going to replace -5 with 10. And we move 10 up to the top. And now our heap looks something like this. And so if you recall, the reason we do this is to make deletion easier on us, right? Because removing this, it's not a huge structural change to our heap, but we're disobeying the min heap property, right? Because previously, the smallest thing was on top, we had a min heap, and everything below 5 was greater than it. And everything below 4 is greater than it. And everything below 5 is greater than it. And everything below -1 was greater than it. And so we saw this min heap property used to be obeyed, but now not so much, right? Now, everything below 10 is definitely not greater than 10. So we have a problem. We need to move 10 down. And so we're going to swim 10 down. And the first thing this requires is looking at 10's children and swapping places with one of them. We're going to swap places with the smaller child. And so -1 comes up on top. And now 10 is here. And this is what we look like. And then we have to continue moving 10 down, right? Because the min heap property is still not obeyed. 10 is still greater than some of its children, both 0 and 0. And so we have to swap 10 down. And this is actually an interesting place where it doesn't matter which child you swap 10 down with, right? All that is required is that we put the smallest child on top, and 0 and 0 are the same. And so it doesn't really matter, but we can just say maybe 10 swaps with the left 0. And so it looks like this. And so that is the swap that happens. But if we go and compare to the original, our before and our after, we see that the 10 is equivalently in like this spot, right? It's like analogous. And whether we had swapped 10 with the left 0 or the right 0, we see 10 would have been in one of these two spots, or in other words, in a position previously occupied by a 0. And that is this whole problem. So thank you for sticking around for this explanation, and enjoy your day.